Hello, it's Stat 135, Lecture 16. So last time we were talking about uniformly most powerful tests, which extends the optimality of simple hypotheses to composite hypotheses. However, usually they're only good for a limited range of alternative values, which unfortunately aren't the values that you often need. So they have actually limited use. We'll see how to get around this problem, however, using what's called a generalized likelihood ratio test. So today we're going to talk about section 9.3, duality of confidence intervals and hypothesis tests, as well as section 9.4 on the generalized likelihood ratio test. So section 9.3, the duality of confidence intervals and hypothesis tests. So in words, the test statistic for a level alpha hypothesis test with null theta is theta 0 lies in the acceptance region if and only if theta 0 lies in 100 minus alpha % CI for theta. So to see an example of this, say that x1, xn are IID normal mu sigma squared, where sigma squared is known. So the null is that mu is mu 0, and the alternative is that mu is not mu 0. So we're going to fix alpha, the level of significance, and okay, and we'll see later today that the acceptance region of a generalized likelihood ratio test for this hypothesis test is x bar in mu 0 plus or minus z alpha over 2 sigma over square root of n. In other words, it has this picture, the acceptance region is in the highlighted green area here, and this is a graph of the null distribution under the assumption that mu is mu naught, and it has SD sigma over square root of n. So notice that mathematically the following two inequalities are equivalent. So x bar is between mu 0 and mu 0 minus z alpha over 2 sigma over square root of n, and mu 0 plus z alpha over 2 sigma square root of n. And the confidence interval mu 0 is between x bar minus z alpha over 2 sigma over square root of n, and x bar plus z alpha over 2 sigma over square root of n. So it should be quite easy for you to see that you can go from one inequality to the other and back. It follows that we can accept the null when x bar is in the acceptance region, or equivalently when mu 0 is in the 100 1 minus alpha % CI for mu. In other words, mu 0 is in x bar plus or minus z alpha over 2 sigma over square root of n. So for more general proof that will work for any CI HT, see theorem AB in section 9.3 in the book, but I'm not going to go over it here. So we're on to section 9.4, the generalized likelihood ratio test. So most hypothesis tests are not simple, and the uniformly most powerful test often doesn't work in the range of alternative values you need. So for composite hypotheses, we usually use the generalized likelihood ratio test. So we're going to let omega be a disjoint union of two sets, omega 0 and omega 1. And our null is going to be that theta is in omega 0, and the alternative is going to be that theta is in omega 1. And we're going to define lambda to be the max over all theta in omega 0 of the likelihoods, divided by the max over all theta in the entire omega likelihoods. so the denominator is precisely the likelihood of the ML, because that theta that maximizes the likelihood is the definition of the ML. And so we'll just plug that into the likelihood then of theta. And so the generalized likelihood ratios test says reject the null if lambda is less than c, otherwise accept. And c here depends on alpha. So the generalized likelihood ratio test makes sense, right? Because you would reject if the numerator of lambda is small relative to the denominator. So because if the null is true, the numerator would be large. So let's see an example. So say x1 to xn is IID normal with sigma squared known. The null is that mu is mu zero, so mu zero is a fixed number. H1 is mu is not mu zero. So here we have omega zero is mu zero, and omega 1 is everything outside of that. So omega is mu zero union omega 1. Omega 0 plus omega 1, which is all of R. And so we can find the numerator and denominator of lambda. So the numerator is just the likelihood of mu zero, because omega 0 is just mu zero. And so I know the likelihood for it's a joint likelihood for my normals, and that's the equation I've written out here. And so let me just write this a little more clearly here. And then for the denominator, similarly, we have this formula here. And notice that the 1 over sigma square root 2 pi to the nth power cancels in the numerator and the denominator, and we get lambda is equal to the expression given here. I'll highlight that. And so now lambda is less than c if and only if minus 2 log lambda is greater than minus 2 log c. And so minus 2 log lambda is, with a bit of algebra you can see, is n over sigma squared x bar minus mu 0 squared. And so minus 2 log lambda is greater than k if and only if x bar minus mu 0 over sigma over square root of n squared is greater than k. But this is just z squared, which is a chi squared with 1 degree of freedom, assuming that the expectation of x is mu 0, or equivalently the expectation of x bar is mu 0, which is true by the null. So you can see this in a picture here. So right, so our rejection region, so that here is the distribution for minus 2 log lambda, which is a chi squared with 1 degree of freedom. And we're going to reject if the p-value is less than alpha. So our cutoff here is chi squared with 1 degree of freedom alpha, or in R it's q chi square 1 minus alpha degrees of freedom equals 1. So the generalized likelihood ratio test says reject the null if minus 2 log lambda is greater than chi squared with 1 degree of freedom alpha. So note that you can also use x bar as a TS, since x bar is normal, and so we know the distribution of x bar. And you can see very easily that we're going to get exactly the same test. So you can just take the square root of both sides, and you get that the absolute value of x bar minus mu 0 is greater than z alpha over 2 sigma over square root of n. So the acceptance region is the highlighted equation here. It's just what we had above. So this, just know that the fact that x bar is a distribution we know is only true. Well, I'm sorry. So this works out nicely because it's x bar. For some other distribution, it wouldn't work as nicely. But you can always use the fact that minus 2 log lambda is a chi squared, and here is the theorem. So if the likelihood function of x is smooth, then the null distribution of minus 2 log lambda is a chi squared with degrees of freedom dimension of omega minus dimension of omega 0. So in our example, omega is r, and omega 0 is just a single point, which is dimension 0. So one more example, pollsters want to know the fraction of population theta that supports a particular political bill. They want to test if theta is 1/2 versus theta is not 1/2. What's the GLRT of a 5% level of significance? So here x1 to xn is IID Bernoulli theta. The joint likelihood I've written down. Remember that the ML is x bar, and our null and alternative hypotheses are described here. Omega is the interval 0, 1, and lambda is the likelihood of 1/2 over the likelihood of x bar. And I've written out what this is, and this is something that you can calculate from your data, and hence find minus 2 log lambda. So the generalized likelihood ratio test is reject for minus 2 log lambda is greater than k, and accept otherwise. So for large n, minus 2 log lambda is chi squared with 1 degree of freedom, and our cutoff will be chi squared 1 with alpha 0.05, which is 3.84. So the generalized likelihood ratio says reject if minus 2 log lambda is greater than 3.84, accept otherwise, and minus 2 log lambda is a number that you can calculate from your data. Okay, so I wish you have a great weekend, and I'll see you next week.